Optical fiber. An optical fiber, or fiber in British English, is a flexible, transparent fiber made by drawing glass, silica, or plastic to a diameter slightly thicker than that of a human hair. Optical fibers are used most often as a means to transmit light between the two ends of the fiber and find wide usage in fiber-optic communications, where they permit transmission over longer distances and at higher bandwidths data transfer rates than electrical cables. Fibers are used instead of metal wires because signals travel along them with less loss. In addition, fibers are immune to electromagnetic interference, a problem from which metal wires suffer. Fibers are also used for illumination and imaging, and are often wrapped in bundles so they may be used to carry light into or images out of confined spaces, as in the case of a fiberscope. Specially designed fibers are also used for a variety of other applications, some of them being fiber, optic sensors, and fiber lasers. Optical fibers typically include a core surrounded by a transparent cladding material with a lower index of refraction. Light is kept in the core by the phenomenon of total internal reflection, which causes the fiber to act as a waveguide. Fibers that support many propagation paths or transverse modes are called multi-mode fibers, while those that support a single mode are called single-mode fibers, SMF. Multi-mode fibers generally have a wider core diameter and are used for short-distance communication links and for applications where high power must be transmitted. Single-mode fibers are used for most communication links longer than 1,000 meters, 3,300 ft. Being able to join optical fibers with low loss is important in fiber optic communication. This is more complex than joining electrical wire or cable and involves careful cleaving of the fibers, precise alignment of the fiber cores, and the coupling of these aligned cores. For applications that demand a permanent connection, a fusion splice is common. In this technique, an electric arc is used to melt the ends of the fibers together. Another common technique is a mechanical splice, where the ends of the fibers are held in contact by mechanical force. Temporary or semi-permanent connections are made by means of specialized optical fiber connectors. The field of applied science and engineering concerned with the design and application of optical fibers is known as fiber optics. The term was coined by Indian-American physicist Narinder Singh Kapany, who is widely acknowledged as the father of fiber optics. History. Guiding of light by refraction, the principle that makes fiber optics possible, was first demonstrated by Daniel Colladin and Jacques Babinet in Paris in the early 1840s. John Tyndall included a demonstration of it in his public lectures in London 12 years later. Tyndall also wrote about the property of total internal reflection in an introductory book about the nature of light in 1870. When the light passes from air into water, the refracted ray is bent towards the perpendicular. When the ray passes from water to air, it is bent from the perpendicular. If the angle which the ray in water encloses with the perpendicular to the surface be greater than 48 degrees, the ray will not quit the water at all, it will be totally reflected at the surface. The angle which marks the limit where total reflection begins is called the limiting angle of the medium. For water this angle is 48°27, for flint glass it is 38°41, while for a diamond it is 23°42. In the late 19th and early 20th centuries, light was guided through bent glass rods to illuminate body cavities. Practical applications such as close internal illumination during dentistry appeared early in the 20th century. Image transmission through tubes was demonstrated independently by the radio experimenter Clarence Hansell and the television pioneer John Logie Baird in the 1920s. In the 1930s, Heinrich Lem showed that one could transmit images through a bundle of unclad optical fibers and used it for internal medical examinations, but his work was largely forgotten. In 1953, Dutch scientist Bram van Heel first demonstrated image transmission through bundles of optical fibers with a transparent cladding. That same year, Harold Hopkins and Narinder Singh Kapany at Imperial College in London succeeded in making image-transmitting bundles with over 10,000 fibers, and subsequently achieved image transmission through a 75 cm long bundle which combined several thousand fibers. The first practical fiber-optic semi-flexible gastroscope was patented by Basil Herskovits, C. Wilbur Peters, and Lawrence E. Curtis, researchers at the University of Michigan, in 1956. In the process of developing the gastroscope, Curtis produced the first glass-clad fibers. Previous optical fibers had relied on air or impractical oils and waxes as the low-index cladding material. Kapany coined the term fiber optics, wrote a 1960 article in Scientific American that introduced the topic to a wide audience, and wrote the first book about the new field. The first working fiber optic data transmission system was demonstrated by German physicist Manfred Borner at Telefunken Research Labs in Ulm in 1965, which was followed by the first patent application for this technology in 1966. In 1968, NASA used fiber optics in the television cameras that were sent to the moon. At the time, the use in the cameras was classified confidential, and employees handling the cameras had to be supervised by someone with an appropriate security clearance. Charles K. Cow and George A. Hockham of the British company Standard Telephones and Cables STC were the first, in 1965, to promote the idea that the attenuation in optical fibers could be reduced below 20 decibels per kilometer dB/km, making fibers a practical communication medium. They proposed that the attenuation in fibers available at the time was caused by impurities that could be removed, rather than by fundamental physical effects such as scattering. They correctly and systematically theorized the light loss properties for optical fiber and pointed out the right material to use for such fibers: silica glass with high purity. This discovery earned Cow the Nobel Prize in Physics in 2009. The crucial attenuation limit of 20 dB/km was first achieved in 1970 by researchers Robert D. Mara, Donald Keck, Peter C. Schultz, and Frank Zimmer working for American glassmaker Corning Glass Works. They demonstrated a fiber with 17 dB/km attenuation by doping silica glass with titanium. A few years later, they produced a fiber with only 4 dB/km attenuation using germanium dioxide as the core dopant. In 1981, General Electric produced fused quartz ingots that could be drawn into strands 25 miles 40 km long. Initially, high-quality optical fibers could only be manufactured at 2 meters per second. Chemical engineer Thomas Mensa joined Corning in 1983 and increased the speed of manufacture to over 50 meters per second, making optical fiber cables cheaper than traditional copper ones. These innovations ushered in the era of optical fiber telecommunication. The Italian research center CSELT worked with Corning to develop practical optical fiber cables, resulting in the first metropolitan fiber optic cable being deployed in Turin in 1977. CSELT also developed an early technique for splicing optical fibers called spring groove. Attenuation in modern optical cables is far less than in electrical copper cables, leading to long-haul fiber connections with repeater distances of 7,150 km 4393 mi. The erbium-doped fiber amplifier, which reduced the cost of long-distance fiber systems by reducing or eliminating optical repeaters, was developed by two teams led by David N. Payne of the University of Southampton and Emmanuel de Zervire at Bell Labs in 1986 and 1987. The emerging field of photonic crystals led to the development in 1991 of photonic crystal fiber, which guides light by diffraction from a periodic structure rather than by total internal reflection. The first photonic crystal fibers became commercially available in 2000. Photonic crystal fibers can carry higher power than conventional fibers, and their wavelength-dependent properties can be manipulated to improve performance. Uses: communication, Optical fiber is used as a medium for telecommunication and computer networking because it is flexible and can be bundled as cables. It is especially advantageous for long-distance communications because infrared light propagates through the fiber with much lower attenuation compared to electricity in electrical cables. This allows long distances to be spanned with few repeaters. 10 or 40 Gbps is typical in deployed systems. Through the use of wavelength division multiplexing WDM, each fiber can carry many independent channels, each using a different wavelength of light. The net data rate without overhead bytes per fiber is the per-channel data rate reduced by the efficacy overhead multiplied by the number of channels, usually up to 80 in commercial dense WDM systems as of 2008. For short-distance applications, such as a network in an office building, see fiber to the office, fiber-optic cabling can save space in cable ducts. This is because a single fiber can carry much more data than electrical cables, such as standard Category 5 cable, which typically runs at 100 Mbit/s or 1 Gbit/s speeds. Fibers are often also used for short-distance connections between devices. For example, most high-definition televisions offer a digital audio-optical connection. This allows the streaming of audio over light using the S/PDIF protocol over an optical toslink connection. Sensors. Fibers have many uses in remote sensing. In some applications, the sensor is itself an optical fiber. Fibers are used to channel radiation to a sensor where it is measured. In other cases, fiber is used to connect a sensor to a measurement system. Optical fibers can be used as sensors to measure strain, temperature, pressure, and other quantities by modifying a fiber so that the property being measured modulates the intensity, phase, polarization, wavelength, or transit time of light in the fiber. Sensors that vary the intensity of light are the simplest since only a simple source and detector are required. A particularly useful feature of such fiber optic sensors is that they can, if required, provide distributed sensing over distances of up to 1 meter. In contrast, highly localized measurements can be provided by integrating miniaturized sensing elements with the tip of the fiber. These can be implemented by various micro and nanofabrication technologies such that they do not exceed the microscopic boundary of the fiber tip, allowing for such applications as insertion into blood vessels. Extrinsic fiber optic sensors use an optical fiber cable, normally a multi-mode one. A major benefit of extrinsic sensors is their ability to reach otherwise inaccessible places. An example is the measurement of temperature inside jet engines by using a fiber to transmit radiation into a pyrometer outside the engine. Extrinsic sensors can be used in the same way to measure the internal temperature of electrical transformers, where the extreme electromagnetic fields present make other measurement techniques impossible. Extrinsic sensors measure vibration, rotation, displacement, velocity, acceleration, torque, and torsion. A solid-state version of the gyroscope, using the interference of light, has been developed. The fiber-optic gyroscope, FOG, has no moving parts and exploits the Sagnac effect to detect mechanical rotation. Common uses for fiber-optic sensors include advanced intrusion detection security systems. The light is transmitted along a fiber optic sensor cable placed on a fence, pipeline, or communication cabling, and the returned signal is monitored and analyzed for disturbances. This returned signal is digitally processed to detect disturbances and trip an alarm if an intrusion has occurred. Optical fibers are widely used as components of optical chemical sensors and optical biosensors. Power transmission. Optical fiber can be used to transmit power using a photovoltaic cell to convert the light into electricity. While this method of power transmission is not as efficient as conventional ones, it is especially useful in situations where it is desirable not to have a metallic conductor, as in the case of use near MRI machines, which produce strong magnetic fields. Other examples are for powering electronics in high-powered antenna elements and measurement, devices used in high-voltage transmission equipment. Other uses: optical fibers are used as light guides in medical and other applications where bright light needs to be shone on a target without a clear line of sight path. Many microscopes use fiber-optic light sources to provide intense illumination of samples being studied. Optical fiber is also used in imaging optics. A coherent bundle of fibers is used, sometimes along with lenses, for a long, thin imaging device called an endoscope, which is used to view objects through a small hole. Medical endoscopes are used for minimally invasive exploratory or surgical procedures. Industrial endoscopes, see fiberscope or Gyroscope, are used for inspecting anything hard to reach, such as jet engine interiors. In some buildings, optical fibers route sunlight from the roof to other parts of the building, see non-imaging optics. Optical fiber lamps are used for illumination in decorative applications, including signs, art, toys, and artificial Christmas trees. Optical fiber is an intrinsic part of the light-transmitting concrete building product Refraction. Optical fiber can also be used in structural health monitoring. This type of sensor is able to detect stresses that may have a lasting impact on structures. It is based on the principle of measuring analog attenuation. In spectroscopy, optical fiber bundles transmit light from a spectrometer to a substance that cannot be placed inside the spectrometer itself in order to analyze its composition. A spectrometer analyzes substances by bouncing light off and through them. By using fibers, a spectrometer can be used to study objects remotely. An optical fiber doped with certain rare earth elements such as erbium can be used as the gain medium of a laser or optical amplifier. Rare earth-doped optical fibers can be used to provide signal amplification by splicing a short section of doped fiber into a regular undoped optical fiber line. The doped fiber is optically pumped with a second laser wavelength. Both wavelengths of light are transmitted through the doped fiber, which transfers energy from the second pump wavelength. The process that causes the amplification is stimulated emission. Optical fiber is also widely exploited as a nonlinear medium. The glass medium supports a host of nonlinear optical interactions, and the long interaction lengths possible in fiber facilitate a variety of phenomena, which are harnessed for applications and fundamental investigation. Conversely, fiber nonlinearity can have deleterious effects on optical signals, and measures are often required to minimize such unwanted effects. Optical fibers doped with a wavelength shifter collect scintillation light in physics experiments. Fiber optic sights for handguns, rifles, and shotguns use pieces of optical fiber to improve the visibility of markings on the sight. Principle of operation. An optical fiber is a cylindrical dielectric waveguide, non-conducting waveguide that transmits light along its axis through the process of total internal reflection. The fiber consists of a core surrounded by a cladding layer, both of which are made of dielectric materials. To confine the optical signal in the core, the refractive index of the core must be greater than that of the cladding. The boundary between the core and cladding may either be abrupt, in step index fiber, or gradual, in graded index fiber. Light can be fed into optical fibers using lasers or LED. Fiber is immune to electrical interference. There is no crosstalk between signals in different cables and no pickup of environmental noise. Information traveling inside the optical fiber is even immune to electromagnetic pulses generated by nuclear devices. Fiber cables do not conduct electricity, which makes fiber useful for protecting communications equipment in high-voltage environments, such as power generation facilities or applications prone to lightning strikes. The electrical isolation also prevents problems with ground loops. Because there is no electricity in optical cables that could potentially generate sparks, they can be used in environments where explosive fumes are present. Wiretapping in this case, fiber tapping is more difficult compared to electrical connections. Fiber cables are not targeted for metal theft. In contrast, copper cable systems use large amounts of copper and have been targeted since the 2000s commodities boom. Refractive index. The refractive index is a way of measuring the speed of light in a material. Light travels fastest in a vacuum, such as in outer space. The speed of light in a vacuum is about 300,000 kilometers, 186,000 miles per second. The refractive index of a medium is calculated by dividing the speed of light in a vacuum by the speed of light in that medium. The refractive index of a vacuum is therefore 1 by definition. A typical single-mode fiber used for telecommunications has a cladding made of pure silica with an index of 1.444 at 1500 nm and a core of doped silica with an index around 1.4475. The larger the index of refraction, the slower light travels in that medium. From this information, a simple rule of thumb is that a signal using optical fiber for communication will travel at around 200,000 kilometers per second. Thus, a phone call carried by fiber between Sydney and New York, a 16,000 kilometer distance, means that there is a minimum delay of 80 milliseconds, about 1/12 \displaystyle\tfrac 1/12 of a second between when one caller speaks and the other hears. Total internal reflection. When light traveling in an optically dense medium hits a boundary at a steep angle larger than the critical angle for the boundary, the light is completely reflected. This is called total internal reflection. This effect is used in optical fibers to confine light in the core. Most modern optical fiber is weakly guiding, meaning that the difference in refractive index between the core and the cladding is very small, typically less than 1%. Light travels through the fiber core, bouncing back and forth off the boundary between the core and cladding. Because the light must strike the boundary with an angle greater than the critical angle, only light that enters the fiber within a certain range of angles can travel down the fiber without leaking out. This range of angles is called the acceptance cone of the fiber. There is a maximum angle from the fiber axis at which light may enter the fiber, so the sign of this maximum angle is the numerical aperture Na of the fiber. Fiber with a larger Na requires less precision to splice and work with than fiber with a smaller Na. The size of this acceptance cone is a function of the refractive index difference between the fiber's core and cladding. Single-mode fiber has a small Na. Multi-mode fiber. Fiber with large core diameter greater than 10 micrometers may be analyzed by geometrical optics. Such fiber is called multi-mode fiber. From the electromagnetic analysis, see below. In a step index multi-mode fiber, rays of light are guided along the fiber core by total internal reflection. Rays that meet the core cladding boundary at an angle measured relative to a line normal to the boundary greater than the critical angle for this boundary are completely reflected. The critical angle is determined by the difference in index of refraction between the core and cladding materials. Rays that meet the boundary at a low angle are refracted from the core into the cladding where they terminate. The critical angle determines the acceptance angle of the fiber, often reported as a numerical aperture. A high numerical aperture allows light to propagate down the fiber in rays both close to the axis and at various angles, allowing efficient coupling of light into the fiber. However, this high numerical aperture increases the amount of dispersion as rays at different angles have different path lengths and therefore take different amounts of time to traverse the fiber. In graded index fiber, the index of refraction in the core decreases continuously between the axis and the cladding. This causes light rays to bend smoothly as they approach the cladding, rather than reflecting abruptly from the core cladding boundary. The resulting curved paths reduce multi-path dispersion because high-angle rays pass more through the lower index periphery of the core, rather than the high-index center. The index profile is chosen to minimize the difference in axial propagation speeds of the various rays in the fiber. This ideal index profile is very close to a parabolic relationship between the index and the distance from the axis. Single-mode fiber. Fiber with a core diameter less than about 10 times the wavelength of the propagating light cannot be modeled using geometric optics. Instead, It must be analyzed as an electromagnetic waveguide structure by solution of Maxwell's equations as reduced to the electromagnetic wave equation. The electromagnetic analysis may also be required to understand behaviors such as speckle that occur when coherent light propagates in multi-mode fiber. As an optical waveguide, the fiber supports one or more confined transverse modes by which light can propagate along the fiber. Fiber supporting only one mode is called single-mode or monomode fiber. The behavior of larger core multi-mode fiber can also be modeled using the wave equation, which shows that such fiber supports more than one mode of propagation, hence the name. The results of such modeling of multi-mode fiber approximately agree with the predictions of geometric optics if the fiber core is large enough to support more than a few modes. The waveguide analysis shows that the light energy in the fiber is not completely confined in the core. Instead, especially in single-mode fibers, a significant fraction of the energy in the bound mode travels in the cladding as an evanescent wave. The most common type of single-mode fiber has a core diameter of 8–10 micrometers and is designed for use in the near-infrared. The mode structure depends on the wavelength of the light used, so that this fiber actually supports a small number of additional modes at visible wavelengths. Multi-mode fiber, by comparison, is manufactured with core diameters as small as 50 micrometers and as large as hundreds of micrometers. The normalized frequency V for this fiber should be less than the first zero of the Bessel function J0, approximately 2.405. Special purpose fiber. Some special-purpose optical fiber is constructed with a non-cylindrical core and slash or cladding layer, usually with an elliptical or rectangular cross-section. These include polarization-maintaining fiber and fiber designed to suppress whispering gallery mode propagation. Polarization-maintaining fiber is a unique type of fiber that is commonly used in fiber-optic sensors due to its ability to maintain the polarization of the light inserted into it. Photonic crystal fiber is made with a regular pattern of index variation, often in the form of cylindrical holes that run along the length of the fiber. Such fiber uses diffraction effects instead of or in addition to total internal reflection to confine light to the fiber's core. The properties of the fiber can be tailored to a wide variety of applications. Mechanisms of attenuation. Light scattering. The propagation of light through the core of an optical fiber is based on total internal reflection of the light wave. Rough and irregular surfaces, even at the molecular level, can cause light rays to be reflected in random directions. This is called diffuse reflection or scattering, and it is typically characterized by wide variety of reflection angles. Light scattering depends on the wavelength of the light being scattered. Thus, limits to spatial scales of visibility arise, depending on the frequency of the incident light wave and the physical dimension or spatial scale of the scattering center, which is typically in the form of some specific microstructural feature. Since visible light has a wavelength of the order of 1 micrometer, 1/millionth of a meter, scattering centers will have dimensions on a similar spatial scale. Thus, attenuation results from the incoherent scattering of light at internal surfaces and interfaces. In polycrystalline materials, such as metals and ceramics, in addition to pores, most of the internal surfaces or interfaces are in the form of grain boundaries that separate tiny regions of crystalline order. It has recently been shown that when the size of the scattering center or grain boundary is reduced below the size of the wavelength of the light being scattered, the scattering no longer occurs to any significant extent. This phenomenon has given rise to the production of transparent ceramic materials. Similarly, the scattering of light in optical quality glass fiber is caused by molecular level irregularities, compositional fluctuations in the glass structure. Indeed, one emerging school of thought is that a glass is simply the limiting case of a polycrystalline solid. Within this framework, domains exhibiting various degrees of short-range order become the building blocks of both metals and alloys, as well as glasses and ceramics. Distributed both between and within these domains are microstructural defects that provide the most ideal locations for light scattering. This same phenomenon is seen as one of the limiting factors in the transparency of IR missile domes. At high optical powers, scattering can also be caused by nonlinear optical processes in the fiber. UV-vis IR absorption. In addition to light scattering, attenuation or signal loss can also occur due to selective absorption of specific wavelengths in a manner similar to that responsible for the appearance of color. Primary material considerations include both electrons and molecules as follows. At the electronic level, it depends on whether the electron orbitals are spaced or quantized such that they can absorb a quantum of light or photon of a specific wavelength or frequency in the ultraviolet, UV, or visible ranges. This is what gives rise to color. At the atomic or molecular level, it depends on the frequencies of atomic or molecular vibrations or chemical bonds, how close packed its atoms or molecules are, and whether or not the atoms or molecules exhibit long-range order. These factors will determine the capacity of the material transmitting longer wavelengths in the infrared IR, far, radio, and microwave ranges. The design of any optically transparent device requires the selection of materials based upon knowledge of its properties and limitations. The lattice absorption characteristics observed at the lower frequency regions mid-IR to far infrared wavelength range define the long wavelength transparency limit of the material. They are the result of the interactive coupling between the motions of thermally induced vibrations of the constituent atoms and molecules of the solid lattice and the incident light wave radiation. Hence, all materials are bounded by limiting regions of absorption caused by atomic and molecular vibrations bond stretching in the far infrared tenon. Thus, multi-phonon absorption occurs when two or more phonons simultaneously interact to produce electric dipole moments with which the incident radiation may couple. These dipoles can absorb energy from the incident radiation, reaching a maximum coupling with the radiation when the frequency is equal to the fundamental vibrational mode of the molecular dipole, e.g., CO bond in the far infrared, or one of its harmonics. The selective absorption of infrared IR light by a particular material occurs because the selected frequency of the light wave matches the frequency or an integer multiple of the frequency at which the particles of that material. Since different atoms and molecules have different natural frequencies of vibration, they will selectively absorb different frequencies or portions of the spectrum of infrared IR light. Reflection and transmission of light waves occur because the frequencies of the light waves do not match the natural resonant frequencies of vibration of the object. When IR light of these frequencies strikes an object, the energy is either reflected or transmitted. Loss budget. Attenuation over a cable run is significantly increased by the inclusion of connectors and splices. When computing the acceptable attenuation loss budget between a transmitter and a receiver, one includes dB loss due to the type and length of fiber optic cable, dB loss introduced by connectors and dB loss introduced by splices. Connectors typically introduce 0.3 dB per connector on well-polished connectors. Splices typically introduce less than 0.3 dB per splice. The total loss can be calculated by loss equals dB loss per connector x number of connectors plus dB loss per splice x number of splices plus dB loss per kilometer x kilometers of fiber, where the dB loss per kilometer is a function of the type of fiber and can be found in the manufacturer's specifications. For example, typical 1550 nm single-mode fiber has a loss of 0.4 dB per kilometer. The calculated loss budget is used when testing to confirm that the measured loss is within the normal operating parameters. Manufacturing. Materials. Glass optical fibers are almost always made from silica, but some other materials, such as fluorozirconate, fluoroluminate, and chalcogenide glasses as well as crystalline materials like sapphire, are used for longer wavelength infrared or other specialized applications. Silica and fluoride glasses usually have refractive indices of about 1.5, but some materials such as the chalcogenides can have indices as high as 3. Typically, the index difference between core and cladding is less than 1%. Plastic optical fibers (POF) are commonly step index multi-mode fibers with a core diameter of 0.5 mm or larger. POF typically have higher attenuation coefficients than glass fibers, 1 dB/m or higher, and this high attenuation limits the range of POF-based systems. Silica exhibits fairly good optical transmission over a wide range of wavelengths. In the near-infrared near-IR portion of the spectrum, particularly around 1.5 mm, silica can have extremely low absorption and scattering losses of the order of 0.2 dB/km. Such remarkably low losses are possible only because ultra-pure silicon is available, it being essential for manufacturing integrated circuits and discrete transistors. A high transparency in the 1.4 mm region is achieved by maintaining a low concentration of hydroxyl groups OH. Alternatively, a high OH concentration is better for transmission in the ultraviolet UV region. Silica can be drawn into fibers at reasonably high temperatures and has a fairly broad glass transformation range. One other advantage is that fusion splicing and cleaving of silica fibers is relatively effective. Silica fiber also has high mechanical strength against both pulling and even bending, provided that the fiber is not too thick and that the surfaces have been well prepared during processing. Even simple cleaving breaking of the ends of the fiber can provide nicely flat surfaces with acceptable optical quality. Silica is also relatively chemically inert. In particular, it is not hygroscopic, does not absorb water. Silica glass can be doped with various materials. One purpose of doping is to raise the refractive index, e.g. with germanium dioxide G(O2) or aluminium oxide Al2O3, or to lower it, e.g. with fluorine or boron trioxide B2O3. Doping is also possible with laser active ions, for example, rare earth doped fibers, in order to obtain active fibers to be used, for example, in fiber amplifiers or laser applications. Both the fiber core and cladding are typically doped, so that the entire assembly core and cladding is effectively the same compound, e.g. an aluminosilicate, germanosilicate, phosphosilicate, or borosilicate glass. Particularly for active fibers, pure silica is usually not a very suitable host glass because it exhibits a low solubility for rare earth ions. This can lead to quenching effects due to clustering of dopant ions. Aluminosilicates are much more effective in this respect. Silica fiber also exhibits a high threshold for optical damage. This property ensures a low tendency for laser-induced breakdown. This is important for fiber amplifiers when utilized for the amplification of short pulses. Because of these properties, silica fibers are the material of choice in many optical applications, such as communications, except for very short distances with plastic optical fiber, fiber lasers, fiber amplifiers, and fiber optic sensors. Large efforts put forth in the development of various types of silica fibers have further increased the performance of such fibers over other materials. Fluoride glass. Fluoride glass is a class of non-oxide optical quality glasses composed of fluorides of various metals. Because of their low viscosity, it is very difficult to completely avoid crystallization while processing it through the glass transition or drawing the fiber from the melt. Thus, although heavy metal fluoride glasses HMFG exhibit very low optical attenuation, they are not only difficult to manufacture, but are quite fragile and have poor resistance to moisture and other environmental attacks. Their best attribute is that they lack the absorption band associated with the hydroxyl OH group 3000, 200, 3000, 600 cm1, i.e. 2777, 3000, 125 nm or 2.78, 3.13 mm, which is present in nearly all oxide-based glasses. An example of a heavy metal fluoride glass is the Z-blend glass group, composed of zirconium, barium, lanthanum, aluminium, and sodium fluorides. Their main technological application is as optical waveguides in both planar and fiber form. They are advantageous especially in the mid-infrared 2000–5000 nm range. HMFGs were initially slated for optical fiber applications because the intrinsic losses of a mid-IR fiber could in principle be lower than those of silica fibers, which are transparent only up to about 2 mm. However, such low losses were never realized in practice, and the fragility and high cost of fluoride fibers made them less than ideal as primary candidates. Later, the utility of fluoride fibers for various other applications was discovered. These include mid-IR spectroscopy, fiber-optic sensors, thermometry, and imaging. Also, fluoride fibers can be used for guided light wave transmission in media such as YAG yttrium aluminium garnet lasers at 2.9 mm as required for medical applications, e.g., ophthalmology and dentistry. Phosphate glass. Phosphate glass constitutes a class of optical glasses composed of metaphosphates of various metals. Instead of the C-offer tetrahedra observed in silicate glasses, the building block for this glass former is phosphorus pentoxide P2O5, which crystallizes in at least 4 different forms. The most familiar polymorph C figure comprises molecules of ferrotin. Phosphate glasses can be advantageous over silica glasses for optical fibers with a high concentration of doping rare earth ions. A mix of fluoride glass and phosphate glass is fluorophosphate glass. Chalcogenide glass. The chalcogens, the elements in group 16 of the periodic table, particularly sulfur S, selenium C, and tellurium T, react with more electropositive elements, such as silver, to form chalcogenides. These are extremely versatile compounds in that they can be crystalline or amorphous, metallic or semiconducting, and conductors of ions or electrons. Glass containing chalcogenides can be used to make fibers for far infrared transmission. Process. Perform. Standard optical fibers are made by first constructing a large diameter, perform with a carefully controlled refractive index profile, and then pulling the perform to form the long, thin optical fiber. The perform is commonly made by 3 chemical vapor deposition methods: inside vapor deposition, outside vapor deposition, and vapor axial deposition. With inside vapor deposition, the perform starts as a hollow glass tube approximately 40 centimeters, 16 in long, which is placed horizontally and rotated slowly on a lathe. Gases such as silicon tetrachloride CCl4 or germanium tetrachloride GCl4 are injected with oxygen in the end of the tube. The gases are then heated by means of an external hydrogen burner, bringing the temperature of the gas up to 1900 K, 1600 deg C, 3000 deg F, where the tetrachlorides react with oxygen to produce silica or germanium dioxide particles. When the reaction conditions are chosen to allow this reaction to occur in the gas phase throughout the tube volume, in contrast to earlier techniques where the reaction occurred only on the glass surface, this technique is called modified chemical vapor deposition mix. The oxide particles then agglomerate to form large particle chains, which subsequently deposit on the walls of the tube as soot. The deposition is due to the large difference in temperature between the gas core and the wall, causing the gas to push the particles outward. This is known as thermophoresis. The torch is then traversed up and down the length of the tube to deposit the material evenly. After the torch has reached the end of the tube, it is then brought back to the beginning of the tube, and the deposited particles are then melted to form a solid layer. This process is repeated until a sufficient amount of material has been deposited. For each layer, the composition can be modified by varying the gas composition, resulting in precise control of the finished fiber's optical properties. In outside vapor deposition or vapor axial deposition, the glass is formed by flame hydrolysis, a reaction in which silicon tetrachloride and germanium tetrachloride are oxidized by reaction with water H2O in an oxyhydrogen flame. In outside vapor deposition, the glass is deposited onto a solid rod, which is removed before further processing. In vapor axial deposition, a short seed rod is used, and a porous perform, whose length is not limited by the size of the source rod, is built up on its end. The porous perform is consolidated into a transparent, solid perform by heating to about 1800 K 1500 deg, C 2800 deg F. Typical communications fiber uses a circular perform. For some applications, such as double-clad fibers, another form is preferred. In fiber lasers based on double-clad fiber, an asymmetric shape improves the filling factor for laser pumping. Because of the surface tension, the shape is smoothed during the drawing process, and the shape of the resulting fiber does not reproduce the sharp edges of the perform. Nevertheless, careful polishing of the perform is important, since any defects of the perform surface affect the optical and mechanical properties of the resulting fiber. In particular, the perform for the test fiber shown in the figure was not polished well, and cracks are seen with the confocal optical microscope. Drawing. The perform, however constructed, is placed in a device known as a drawing tower, where the perform tip is heated and the optical fiber is pulled out as a string. By measuring the resultant fiber width, the tension on the fiber can be controlled to maintain the fiber thickness. Coatings. Cable construction. In practical fibers, the cladding is usually coated with a tough resin coating and an additional buffer layer, which may be further surrounded by a jacket layer, usually plastic. These layers add strength to the fiber but do not contribute to its optical waveguide properties. Rigid fiber assemblies sometimes put light-absorbing dark glass between the fibers to prevent light that leaks out of one fiber from entering another. This reduces crosstalk between the fibers or reduces flare in fiber bundle imaging applications. Modern cables come in a wide variety of sheathings and armor, designed for applications such as direct burial in trenches, high-voltage isolation, dual use as power lines, installation in conduit, lashing to aerial telephone poles, submarine installation, and insertion in paved streets. Multi-fiber cable usually uses colored coatings and slash or buffers to identify each strand. The cost of small fiber count pole mounted cables has greatly decreased due to the high demand for fiber to the home FTTH installations in Japan and South Korea. Some fiber-optic cable versions are reinforced with aramid yarns or glass yarns as intermediary strength member. In commercial terms, usage of the glass yarns are more cost-effective while no loss in mechanical durability of the cable. Glass yarns also protect the cable core against rodents and termites. Practical issues. Installation. Fiber cable can be very flexible, but traditional fibers loss increases greatly if the fiber is bent with a radius smaller than around 30 mm. This creates a problem when the cable is bent around corners or wound around a spool, making FTTX installations more complicated. Bendable fibers, targeted toward easier installation in home environments, have been standardized as ITU-TG 657. This type of fiber can be bent with a radius as low as 7.5 mm without adverse impact. Even more bendable fibers have been developed. Bendable fiber may also be resistant to fiber hacking, in which the signal in a fiber is surreptitiously monitored by bending the fiber and detecting the leakage. Another important feature of cable is cable's ability to withstand horizontally applied force. It is technically called max tensile strength, defining how much force can be applied to the cable during the installation period. Termination and splicing. Optical fibers are connected to terminal equipment by optical fiber connectors. These connectors are usually of a standard type such as FC, SC-SINT, LC, MTRJ, MPO, or SMA. Optical fibers may be connected to each other by connectors or permanently by splicing, that is, joining two fibers together to form a continuous optical waveguide. The generally accepted splicing method is arc fusion splicing, which melts the fiber ends together with an electric arc. For quicker fastening jobs, a mechanical splice is used. Fusion splicing is done with a specialized instrument. The fiber ends are first stripped of their protective polymer coating as well as the more sturdy outer jacket, if present. The ends are cleaved, cut with a precision cleaver to make them perpendicular, and are placed into special holders in the Fusion Splicer. The splice is usually inspected via a magnified viewing screen to check the cleaves before and after the splice. The splicer uses small motors to align the end faces together and emits a small spark between electrodes at the gap to burn off dust and moisture. Then, the splicer generates a larger spark that raises the temperature above the melting point of the glass, fusing the ends together permanently. The location and energy of the spark is carefully controlled so that the molten core and cladding do not mix, and this minimizes optical loss. A splice loss estimate is measured by the splicer by directing light through the cladding on one side and measuring the light leaking from the cladding on the other side. A splice loss under 0.1 dB is typical. The complexity of this process makes fiber splicing much more difficult than splicing copper wire. Mechanical fiber splices are designed to be quicker and easier to install, but there is still the need for stripping, careful cleaning, and precision cleaving. The fiber ends are aligned and held together by a precision-made sleeve, often using a clear index matching gel that enhances the transmission of light across the joint. Such joints typically have higher optical loss and are less robust than fusion splices, especially if the gel is used. All splicing techniques involve installing an enclosure that protects the splice. Fibers are terminated in connectors that hold the fiber end precisely and securely. A fiber-optic connector is basically a rigid cylindrical barrel surrounded by a sleeve that holds the barrel in its mating socket. The mating mechanism can be push and click, turn and latch bayonet mount, or screw-in threaded. The barrel is typically free to move within the sleeve and may have a key that prevents the barrel and fiber from rotating as the connectors are mated. A typical connector is installed by preparing the fiber end and inserting it into the rear of the connector body. Quick-set adhesive is usually used to hold the fiber securely, and a strain relief is secured to the rear. Once the adhesive sets, the fiber's end is polished to a mirror finish. Various polish profiles are used depending on the type of fiber and the application. For single-mode fiber, fiber ends are typically polished with a slight curvature that makes the mated connectors touch only at their cores. This is called a physical contact PC polish. The curved surface may be polished at an angle to make an angled physical contact APC connection. Such connections have higher loss than PC connections, but greatly reduced back reflection, because light that reflects from the angled surface leaks out of the fiber core. The resulting signal strength loss is called gap loss. APC fiber ends have low back reflection even when disconnected. In the 1990s, terminating fiber optic cables was labor-intensive. The number of parts per connector, polishing of the fibers, and the need to oven bake the epoxy in each connector made terminating fiber optic cables difficult. Today, many connectors types are on the market that offer easier, less labor-intensive ways of terminating cables. Some of the most popular connectors are pre-polished at the factory and include a gel inside the connector. Those two steps help save money on labor, especially on large projects. A cleave is made at a required length to get as close to the polished piece already inside the connector. The gel surrounds the point where the two pieces meet inside the connector for very little light loss. Long-term performance of the gel is a design consideration, so for the most demanding installations, factory pre-polished pigtails of sufficient length to reach the first fusion splice enclosure is normally the safest approach that minimizes on-site labor. Free space coupling. It is often necessary to align an optical fiber with another optical fiber or with an optoelectronic device such as a light-emitting diode, a laser diode, or a modulator. This can involve either carefully aligning the fiber and placing it in contact with the device, or can use a lens to allow coupling over an air gap. Typically, the size of the fiber mode is much larger than the size of the mode in a laser diode or a silicon optical chip. In this case, A tapered or lensed fiber is used to match the fiber mode field distribution to that of the other element. The lens on the end of the fiber can be formed using polishing, laser cutting, or fusion splicing. In a laboratory environment, a bare fiber end is coupled using a fiber launch system, which uses a microscope objective lens to focus the light down to a fine point. A precision translation stage micropositioning table is used to move the lens, fiber, or device to allow the coupling efficiency to be optimized. Fibers with a connector on the end make this process much simpler. The connector is simply plugged into a pre-aligned fiber-optic collimator, which contains a lens that is either accurately positioned with respect to the fiber or is adjustable. To achieve the best injection efficiency into single-mode fiber, the direction, position, size, and divergence of the beam must all be optimized. With good beams, 70 to 90% coupling efficiency can be achieved. With properly polished single-mode fibers, the emitted beam has an almost perfect Gaussian shape even in the far field if a good lens is used. The lens needs to be large enough to support the full numerical aperture of the fiber and must not introduce aberrations in the beam. Aspheric lenses are typically used. Fiber fuse. At high optical intensities above 2 megawatts per square centimeter, when a fiber is subjected to a shock or is otherwise suddenly damaged, a fiber fuse can occur. The reflection from the damage vaporizes the fiber immediately before the break, and this new defect remains reflective so that the damage propagates back toward the transmitter at 13 meters per second for 11 km/h, 28 mph, 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 mph. The open fiber control system, which ensures laser eye safety in the event of a broken fiber, can also effectively halt propagation of the fiber fuse. In situations such as undersea cables, where high power levels might be used without the need for open fiber control, a fiber fuse protection device at the transmitter can break the circuit to keep damage to a minimum. Chromatic dispersion. The refractive index of fibers varies slightly with the frequency of light, and light sources are not perfectly monochromatic. Modulation of the light source to transmit a signal also slightly widens the frequency band of the transmitted light. This has the effect that, over long distances and at high modulation speeds, the different frequencies of light can take different times to arrive at the receiver, ultimately making the signal impossible to discern and requiring extra repeaters. This problem can be overcome in a number of ways, including the use of a relatively short length of fiber that has the opposite refractive index gradient.